This split-screen diagram maps an offline app's download process. The bottom shows a successful sequential flow. The top shows a crash caused by a missing prerequisite exception. It fails by attempting to load Module B while requesting data from a missing Module A. To resolve complex dependencies like this, we use an algorithm called Topological Sort. Controlling the execution sequence dictates whether a system loads safely or throws a fatal error. This directed acyclic graph maps our course modules as nodes. The arrows point from the prerequisite to the dependent module, establishing exactly what must finish before a new task begins. Notice the numeric values appearing next to the nodes. This is the in degree, the exact count of incoming requirements a specific module has. If we try to process a raw list of prerequisite pairs by searching through it every time a module finishes, the algorithm will slow down as the data scales. Instead, we parse those raw pairs into an adjacency list that stores the outgoing connections. Alongside it, the in-degree array tracks the total count of incoming dependencies for each node. By calculating these values first, the system identifies which modules currently have no dependencies remaining. This is our FIFO queue engine. We start by finding any module with an in-degree of 0 and dropping it in. When we pop a module out of the queue, we place it in the final order array. We then simulate its completion by sending signals to its neighbors, subtracting 1 from their in-degrees. Look closely at the frozen state. Module B is in the queue, and Module C's in-degree is 1. What happens to C when B finishes? When B pops from the queue, it removes its outgoing requirement. C's in-degree hits 0, triggering it to drop directly into the queue. This process guarantees that a module only enters the final sequence once every single prerequisite has reached an in-degree of 0. This diagram illustrates a cycle. Module D requires E, and E requires D. Both display a persistent in-degree of 1. Because neither node can reach an in-degree of 0, neither can enter the queue. The algorithm halts prematurely. The queue is empty, but we have not processed all the nodes into the final array. An empty queue paired with leftover nodes is the mathematical proof that your graph contains an unresolvable cycle. This editor displays Kahn's algorithm in C++. A loop parses raw dependencies, building the adjacency list. A while loop then processes the queue until empty. Finally, we compare the final array size against the total initial modules to detect cycles. This cheat sheet summarizes the logic. Because the algorithm evaluates every vertex and every edge exactly once, it runs in big O of V plus E time and space. Kahn's algorithm is the engine used for dependency resolution in every major package manager and software build system.